In this problem, we have a person that's standing on a flat car, and it's moving with respect to the ground. He's throwing a ball through a hoop, which is stationary with respect to the ground. Let's draw a picture and see what's happening. We've got a flat car that our person is standing on, and there's a hoop that's stationary relative to the ground. And our person throws the ball with a constant velocity with respect to himself. So he throws the ball consistently, I should say, not constant, consistently at 10.8 meters per second with respect to himself. So the ball is going to go at some angle here. And it wants to go through the hoop and then down the other side. So that's our projectile motion. Now we're given a little bit more information. The car is moving at a speed of 9.1 meters per second, and above the release point, if this is y equals 0, then this is 4.9 meters. So there's a height of 4.9 meters. Here's our y equals 0. And so in order to solve this problem, let's start out with some assumptions. This is a projectile motion problem. So if there's no air resistance, then the motion in the x direction has no acceleration. It's constant velocity. And only the motion in the y direction we have to deal with the acceleration of gravity working on the projectile. Now let's set our positive. I've already set a y equals 0, and our positive direction will be up. Okay, so let's take a look at the y motion. The reason we want to look at the y motion is because that all happens. There's no each frame of reference has the same y motion. There's no change in the frame of reference in the y direction, only in the x direction. So the y direction is a little simpler. So we need to fill in our table here. Our initial and final positions, our initial and final velocities in the y direction, the acceleration, and the time. So we know it starts at 0. It ends up 4.9 meters in the positive direction. We really are looking for our initial velocity. We know the acceleration is 9.8 meters per second squared in the negative direction. We don't know time. We don't know initial velocity. And if we didn't know the final velocity, we wouldn't be able to solve this. But we do know the final velocity. We're given that as the ball passes through the hoop, it only has a horizontal component of velocity. That means its Vy final has to be 0. So I'm going to pick an equation that's missing time, and I'm going to plug in everything I know and solve for the one variable I don't know. So V final squared is V initial squared plus 2a. These are all, of course, in the y direction. Delta y. 0 is my V initial squared plus 2. My acceleration is negative 9.8. And 4.9 is my delta y. So I've got V squared is 96, and V initial in the y direction is 9.8 meters per second. Now I can solve for t. V final equals V initial plus AT. And we get t is 1 second. So we know our initial velocity in the y direction, and we know our time. Let's draw a little picture of what the velocity is going to look like. Initial velocity in the y direction is 9.8. We just solved for that. We know that the person always throws the ball with a speed of 10.8. And so what we're looking for now is V sub x. So this is a right triangle. V sub x squared plus 9.8 squared has to equal 10.8 squared. And that gives us an x velocity of 4.54 meters per second. So we're interested in what the speed is relative to the hoop. This is the x speed relative to the flat car, right? Relative to the person. So relative to the hoop, we say V sub x is the velocity of the ball relative to the flat car plus the velocity of the flat car relative to the ground, and this is the velocity of the ball relative to the ground. So the distance in front of the hoop that the person has to release the ball is 13.6 multiplied by 1 second, and we get 13.6 meters. That would be this distance where the person has to release the ball so it goes through the hoop. The last thing we want to do is take a quick look at what the angle is to the two observers, the observer in the flat car and the observer on the ground. So with respect to the flat car, and with respect to the ground, in both cases we have a y velocity of 9.8. In the flat car, the x velocity is 4.54, and the speed of the projectile was 10.8. So what we really are interested in is this angle theta, and theta is the inverse tangent of 9.8 over 4.54, which is 65.1 degrees. And with respect to the ground, the y velocity is still 9.8, but now instead of 4.5, we have 13.6 as our x velocity. That means that the velocity with respect to the ground is actually 19.3 meters per second, and the angle is the inverse tangent of 9.8 over 13.6, which is 35.8 degrees. So it makes sense, I think, let's take a look, that with respect to the ground, the ball should be moving much faster, because not only is the ball being thrown with some velocity, but the ball had some velocity to begin with. So it gains some extra velocity and extra action due to the initial motion of the cart. And so its overall speed is quicker, and its x velocity is bigger due to the velocity addition part of the problem.